Eric, Alexis. All right, perfect. All right, let's go ahead and move on. Thank you so much for those who are participating. So let's take a look at our schedule for this week. We are in week 8. I cannot believe it. Week 8 of our 13 weeks together. We are in day 33 of our 60-day adventure. We are Monday, January 25th. Our topic is 4A chemical reactions. That means we are starting unit 4, peeps. Oh my goodness gracious, we're moving along as we speak. So starting unit 4. So let's go ahead and take a look at our new unit. Our new unit is chemical reactions. We're going to talk a little bit about chemical reactions and all different types of things. And I like that little mole there, Mrs. Larkin. The little mole. We'll talk about a mole in a couple of lessons down the road. So let's go ahead and take a look at this. We're going to define chemical reactions. We're going to identify the components of a chemical reaction. We're going to explain the differences between endothermic and exothermic chemical reactions and provide examples of reactions, all demonstrating it through our 4A notes, okay? Our 4A notes. So let's go ahead and take a look. Obviously, in the chat box, and we're going to go ahead and put that in the chat box, but we're going to put your notes, grab that link, start your quiz, and raise your hand when you have that quiz open. If you are watching this recording, click the grades tab, scroll down to 4A notes, and start your quiz. Now, remember, one of those links is going to work. One of them is not. So if you not sure which teacher it is, try both of them. One of them is going to work. Once you have it open, grab your, raise your hand when you have started your quiz. Raise your hand when you've started your quiz. I'm going to give you another 15 seconds to get your notes open. Another 15 seconds. I must be hungry because I have like a death grip on my brownies here. Like I can't get rid of them. All right, let's go ahead and check in. Again, we still have a couple of people. I will be checking in with you in just a moment. But let's take it. Gabriel. Oh, thank you so much. Jadelyn. Jaylyn. Thank you, Jaylyn. Derek, Kamari, Michael, Ryan, Christopher, Anthony, Tim. Ooh, people are moving on me. People are moving on me. Thank you, thank you, thank you. So looking for Derek, Kamari, Ryan, Tim, Monty, Annabelle, I think I see you in the chat box. If I don't, let me know. Yeah, that Shelbs, that would be my son. I have him home right now. He's 3 years old, and he is playing with my son's Nerf gun, like dartboard. It like makes music. So Ryan, Tim, Anna, or Alexis, Kale, Julie. Oh, stop moving on me. So Patrick. Does that bug you, Mrs. Larkin, when it starts moving on you? Patrick, Kale, I see you in the chat box. Tim, Ryan, and Kamari. Get your hands up. All right, we're going to go ahead and move on. So what do you think of when you hear the word reaction? What comes to mind when you hear the word reaction? You can give me some words in the chat box. What comes to mind when you hear the word reaction? Subtraction. Okay, opposite. Okay, some people say explode. Okay. Action to something. Good. What else? Against. I like that one. Not even working for me today. What is going on, new row? Against. Okay. Good. Result. I like that. Good. Gabriel has resolution. Interaction. Good. Excellent. I like these words, and these words all do kind of go with the word reaction. Obviously, looking into Unit 4, we're going to be talking about reactions, and especially chemical reactions. So let's take a look about reactions here, chemical reactions.
Awesome. Sorry, I did want to mention that today, tomorrow, and Wednesday we are doing notes, and then we're starting our project on Thursday. So the nice thing about these notes for these few days is they will be going into your project category of your grade book, and so they actually help to boost your project grades. So remember, we will be zeroing out our Unit 3 projects really soon, so it's really helpful to get these notes done. That way you can have a little bit of a boost to your project grade, which can help buffer that if you don't do as well on the project or if you haven't yet turned it in. It's going to be 30 points over these 3 days. To help to help boost your project grades. And you should get great grades on them because we do them together in class. Smiley faces, emojis, if that makes sense. Smiley faces, emojis, if that makes sense in the chat box. Smiley faces, emojis, if that makes sense. Okay. Notes help to boost your project grades. Awesome. All right, so let's go ahead and talk about this. Chemical reactions, we talked about the word reaction. When we talk about chemical reactions, we're talking about a change, right, to substances. So this can occur when we have elements that bond together, bonds in compounds that get broken, or bonds that rearrange themselves to form different substances. I know, Shelbs, the new row is also giving us lots of issues too today, so we'll try to get through it together. All right, so let's go ahead and take a look here. You can see right here an example of bonds coming together. So you can see that these substances A and B, just as examples, are separate, and now you can see they bond together to form a different compound. Again, once they're bonded, we now have completely unique properties. Same thing, we can actually break those and do the reverse. So we can take that bond and actually break it apart so that now they are separate again. Again, these separate elements will now have completely different properties than what they started with as this compound right here. Or bonds can both break and bond at the same time, causing them to rearrange themselves into different substances. So you can see here in both these examples, B and C are switching spots. So in both of these examples, B and C are switching spots. Again, AC is going to be a totally different compound than AB because it's going to have completely unique properties. It's a different chemical. You can see an example down here of hydrogens in pink bonding with nitrogens in yellow to form a different substance. This is going to be NH3 or ammonia, so NH3 right here. And now that they're bonded into this formula, they are now completely different. Ammonia has different properties than hydrogen and nitrogen by themselves. So when chemical changes happen, heat gets absorbed or released. We'll talk a little bit about that at the end of the lesson about heat being absorbed and released.
So let's go ahead and talk about this. So we have our definitions, our term pictures. Remember, A and B will then separate to A plus B, and then obviously doing another one where you have AB plus CD, and then those will go AC plus BD, okay, and then A plus B equaling AB. Remember, let's go ahead and talk about these and use your thin lines. Thank you. My whiteboard tools are on hold. So go ahead and use a thin line. I'll give you about 15 seconds to work on this. Extremely vital. So grab your thin line. Excellent. Thank you. I still need to see more people up on the board. Again, it's important that we are participating here. Good, excellent, perfect. All right, I'm going to stop you right there. Thank you so much for putting your lines up on the board. So let's go ahead and take a look at this. And before I do that, beautiful. We're going to go ahead and look at this. This one obviously is going to be number 1 in your notes, but we're going to look at chemical reactions. The bonds are broken in this particular reaction, whereas when you look over here, the bonds are rearranged. They're rearranged, and then finally those bonds are bonding together. Thank you. Those bonds are bonding together. So that is going to be the answer to number 1 in your notes. I'm going to give you 20 seconds to do that. Again, 20 seconds to get those up. Raise your hand when you are finished. Raise your hand. Go, go, go. Here we go. Let me just check in with a few people. Again, I have already sent out some text messages, so please make sure that you're responding. Please make sure you're responding. So Jadelyn, Tamari, Ryan, Christopher, Tim, Monty, Casimir, thank you. I'm seeing people moving up. Thank you so much. Let me give it just a couple more seconds. Kale, Alexis, I see Annabelle in the chat box. Thank you. Ignacio, Aria, Tim, Christopher, and Ryan and Kamari. Ryan, and Kamari. Please raise your hand. Kamari, Ryan, Christopher, Tim, Arya. I know, I see you, Gabe. Ignacio and Alexis. Awesome. Thank you, Ryan, for letting us know. Thank you for letting us know. No worries, no worries. All right, let's go ahead and move on. I'll continue checking with a few other people.
All right, so let's go ahead and talk a little bit about chemical versus physical changes. This is actually a review from Unit 1. Remember, chemical changes are different from physical changes. Chemical changes occur when the chemicals change. I know it's kind of an obvious obvious description, but when we create different chemicals, that is a chemical change. So for example, iron and oxygen can form rust, which is known as iron oxide. Iron oxide is a totally different chemical from the iron and oxygen that it started with. Same thing with fire. Fire will react with oxygen to form carbon dioxide and heat, as well as it will change the fuel. It'll create something different. So again, we're changing it. It's different chemicals. Now this is different from, for example, during physical changes. Physical changes occur when things are changing, but the chemicals are still the same. For example, ice, water, and steam are all what chemical? Regardless of what they are changing, ice, water, and steam, they're still what chemical? Tell me in the chat box. I'm not asking for raised hands right now. I'm going to go ahead and lower those. I don't need those right now. Ice, water, and steam are all chemically what? What's the chemical formula for ice, water, and steam? Awesome. I see Shelbs in the chat box. I need more participation. Thank you, Camilla. Let's work quickly. Again, I need lots of participation. Otherwise, we're going to go into passing period. Let's take the initiative. Let's participate. Awesome. Thank you. Yeah, this is going to be H2O, right? So whether it is ice, solid H2O, water, liquid H2O, or steam, gaseous H2O, they are all still chemically H2O. And so these are not a chemical change. Smiley faces, emojis, if that makes sense. Chemical changes form different chemicals. Physical changes, the chemicals stay the same. Yeah, it's still water. Exactly, Gabriel. Perfect. All right. So an example here of a chemical change or a chemical reaction is going to be baking soda and vinegar reacting because they form different substances. Again, chemically, we are changing the chemicals. Baking soda is also known as sodium bicarbonate. Vinegar is a chemical called acetic acid. All of your food is chemicals. So whenever someone says, I don't like a food because it has chemicals in it, I roll my eyes because all food is chemicals. Anyways, when these two things react, they're going to form different substances. They form carbon dioxide gas, they form water, and they form a salt called sodium acetate. This is different than table salt. Sodium acetate salt is actually the flavoring that you get in salt and vinegar chips. Do you like them? Yes or no? Tell me in the chat box. Do you like salt and vinegar chips? I like them in small amounts. But yeah, I can't like eat an entire bag because it makes me feel gross. Yeah. Let's go ahead and take a look at this reaction up on the board and make some observations. So I will expect observations in the chat box. Again, we got to participate fast, guys, so that we can catch up on the time we lost at the start of class. So taking a look here, you can see we add a white powder, that's baking soda, to a clear liquid, that was vinegar. And now what do you observe happening? What do you observe happening in this reaction? Again, baking soda, sodium bicarbonate, reacting with vinegar, acetic acid. What happens? Awesome. Yeah, Ame, just try to get here a little bit earlier if you can. Awesome. I see Shelbs, Gabriel making observations. I still am waiting on participation. Again, this seems to be our theme for today. Make sure you're telling me in the chat box, what do you see? Thank you, Miles. Thank you, Daniel. Yeah, so we see bubbles. We see foaming, we see it overflowing. Yes, these bubbles are evidence of CO2. Again, CO2 being a gas, being a completely different compound than what we started with. Sodium bicarbonate and acetic acid are not carbon dioxide. When they react, though, they do form a different new compound. Smiley faces emojis if that makes sense about why that is a chemical reaction. Again, because we're forming something different. Excellent. All right, let's go ahead and take a look at our next question.
Let's take a look at this. So, selecting all the correct statements about chemical changes. Bonds stay the same for the substance, or bonds are broken, formed, or rearranged between the substance. That's one answer, so pick one. Next part of the answer is different chemical substances are formed at the end, or the substance stays chemically the same from start to end. Remember, we're looking at chemical changes here. And that would be an answer for the second part. Third part, an example is freezing carbon dioxide gas into dry ice, or an example is baking soda and vinegar reacting to form carbon dioxide gas, water, or sodium acetate salt. Okay, that would be answer number 3. Okay, I want you to use your, good, whiteboard tools are up. I want you to use your thin box, and go ahead and box the correct answers. Remember, let's work quickly to capture up all the time that we lost in the beginning. So go, go, go. I'm going to give you about 15 seconds. 15 seconds, go. Correct answers, 3 correct answers here. Up on the clock. All right, here we go. So let's take a look at this. Yeah, I think you all did pretty well. I'm going to go ahead and put our whiteboard tools on hold. We have a few artists up on the board. All right, so let's go ahead and take a look at this. I'm going to go to the next page so we can have a clean page. But yeah, you all are pretty correct. Bonds are broken, formed, and rearranged between the substances. You have different chemical substances that are formed at the end, because again, we're talking about chemical changes. And then finally, that example that we just saw in that video is baking soda and vinegar reacting to form that carbon dioxide gas, water, and sodium acetate salt. All right, so excellent job. This is the answer to number 2. This is the answer to number 2. So go ahead and lock in your answers. Lock in your answers. Make sure you're reading them correctly. And I'm going to give you about 20 seconds to do that. Raise your hand when you are finished. Raise your hand when you're finished. Nice try. Quickly and promptly, because we do have to make up that time. Thank you, Annabelle. I see you in the chat box. Excellent. Looking for Kamari, Alan, Dion, Lydia, Ignacio. Thank you, Ignacio. I see some people moving. So Kamari, Aria, Tim, and Ryan. I know that I've talked to you in the chat box, so make sure that you raise your hand. Raise your hand. So Ryan, Tim. Thank you, Ryan. Ryan, just go ahead and keep it up. I know it's kind of finicky. Just when you push it, just push it once, and then it will just stay there. We'll go ahead and lower it, okay? And then Arya and Kamari. Arya and Kamari. Thank you so much. Let's go ahead and move on.
All right, so let's go ahead and talk about some vocabulary with chemical reactions. So chemical reactions have what you start with and they have what you end with. And what you start with are what are called the reactants, the starting substances that are going to undergo the change. The products are going to be the ending substances that get formed from the reaction. The way that I remember this is that reactants, reactants undergo the reaction, and then products are produced. Okay, so they quite literally sound a lot like their root words here. So reactants will undergo the reaction, the products will be what are produced, much like a factory will produce a product that then gets sold to the public. You're going to send out the product, not what you start with. You want to send out what you end with. Okay, now we're going to go ahead and use an analogy, and this analogy we actually started at the start of class in our brain stretch, which is with cake. Now for those of you who aren't familiar with this word, analogy means when we have two things that are not exactly the same, but they have some similarities that help us to better understand a concept, like in this case, a chemical reaction. So here's our analogy. We have some batter ingredients. We're going to go ahead and mix those up, and we're going to introduce heat to them in order to bake a cake. Mrs. Bullitt, I think your mic might be on, just so you know. So in this cake, in this instance, the ingredients, are they more like the reactants or the products? Think about what are the ingredients, what we start with or what we end with. Does that make it like the reactants or the products? Tell me in the chat box. Here is our analogy. We have batter, we heat it, we turn it into a cake. So the ingredients are like the what? Thank you. I see Gabriel in the chat box. I see Miles working hard. Need more participation. Thank you. Yeah, these are going to be like the reactants. Exactly. So ingredients are like the reactants. And then the cake will be the what? Right, we're going to bake it. Baking's the reaction, so the cake is the final what? Tell me in the chat box. If the ingredients are the reactants, what is the cake? Exactly. The cake is going to be the final product. Excellent. All right, now those are two words that we need to know, but we also need to know this third word here, which is a limiting reactant. So a limiting reactant is like you have a bunch of stuff in your cupboard, you have a bunch of ingredients, and you're trying to make something, but you don't have enough of one of the ingredients. So what happens here is a limiting reactant is when one reactant gets completely used up, and so the reaction cannot continue. It prevents us from making more product. It limits the amount that we can make. So it's going to prevent us from making more cakes, for example. All right, smiley faces emojis if that makes sense. It's going to prevent us from making more cakes. Excellent. Thank you. I like that, Octopus. Thank you, Miles. Yes, perfect. All right, this is going to be number 3 in your notes. Go ahead and fill in the blank with the word used. I'm going to have you do this first, and then we're going to go ahead and begin practicing. Again, please participate quickly so that we can make up some time that we lost so we don't have to go too far into passing period. 20 more seconds. Raise your hands for number 3. 10 seconds. All right, I see Gabriel and Annabelle in the chat box waiting on Tay and Tayan, Kamari, Kamari, Jaden, Jaden, Patrick, 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 Kale, Kale, Kale. Aria, waiting on Casimir, Tim, Ryan, raise your hands or send me a chat. Raise your hands or send me a chat. All right, Tim, Aria, Kale. Kamari, make sure you're participating every single time. You either need to send us a chat or raise your hand. Otherwise, you'll be excused. All right, we won't let you back in next time, okay? Gabriel. Oh, sorry, Gabriel's good. Sorry. Ryan, Tim. All right, let's see here. Ryan, Tim, Aria. Thank you, Ryan. And Kale. Kale's good. Okay, looking good. I think we got almost everyone we need. Perfect. Thank you, Tim. All right, let's go ahead and keep on moving. All right, let's go ahead and do this example here. So we have our cake recipe. Our cake recipe here is going to be 1 cup of butter, 2 cups of sugar, 3 cups of flour, and 4 eggs. Now, this is not a real recipe. This would be pretty gross. So let's go ahead and talk about, though, pretending we have all the ingredients we need and only 4 cups of butter, how many cakes could we make with those 4 cups of butter? All right, so our cake needs 1 cup of butter, and we have 4 cups of butter. So how many cakes can we make? I can show you a calculation here. So 4 cups divided by 1 cup of butter per cake. 4 cups of butter that we have, and into each cake we need 1, so 4 divided by 1. How many cakes can we make? Awesome. I see Shelves. I see Gabriel, Camilla, Ignacio. How many cakes can we make? Annabelle, thank you. Taylor, yes, we can make 4 cakes. Perfect. Let's try our next one. We have 10 cups of sugar. Each cake needs 2 cups of sugar. So 10 cups divided by 2 cups of sugar per cake. How many cakes can I make? How many cakes can I make? 10 cups divided by 2 per cake. Yeah, I can make 5 cakes. Perfect. Let's keep going. How about if I have 9 cups of flour and the cake calls for 3 cups of flour? So 9 cups divided by 3 cups per cake. How many cakes can I make? Perfect. Yes, I can make 3. And lastly, if I have 8 eggs and my cake needs 4 eggs, how many cakes can I make? So 8 eggs divided by 4 eggs per cake. How many cakes do I get? Yes, I get 2 cakes. Cool, so we calculated those all individually, but here's the problem. We need to actually look at all the ingredients together. So based on all of our ingredients together, which ingredient am I going to run out of first? Butter, sugar, flour, or eggs? Which ingredient will I run out of first? I know, math is always better when when it's got food involved. What will we run out of first? What is going to be our limiting reactant? Butter, sugar, flour, or eggs. Think about how many cakes they make. Yeah, we absolutely run out of eggs first because after I make how many cakes am I finished? How many cakes can I make before I run out of eggs? How many cakes can I make before I run out of eggs? Yeah, I can only make 2 cakes, right? So I had 8 eggs and I can only make 2 cakes. Once I make up those 2 cakes, I no longer have any eggs. So now I only have flour, sugar, and butter, which a cake it does not make. That would be a pretty gross cake, right? This is going to be the answer to number 4 and number 5. Again, eggs will be our limiting reactant here because after 2 cakes, we are out of eggs. You have 30 seconds to answer both of those. Raise your hands. Go, go, go. 10 seconds remaining. I do like bacon and omelets. I think I like bacon more by itself though, to be honest. Derek, Ryan, Anthony, Timothy, Monty. Annabelle, did I see you in the chat? Annabelle in the chat, please. Gabriel, I see you in the chat. Talking about something else, but I'm assuming you're good. Kale, Lydia, Jaden, Dion, and Kamari. Okay, Ryan's having internet issues. Gotcha. Yummy. Yeah, I buy 2 packs of 18 eggs, and we still usually run out of eggs first. Ryan, sorry, Timothy, Kale, Dion, and Kamari. You're my last four. And then Annabelle, make sure I get you in the chat. Perfect. All right, let's go ahead and keep on moving. All right, so we're going to be talking more about this tomorrow, but chemical equations help to show all of our products and our reactants. So we're going to take a look at aluminum and iron oxide in the thermite reaction, forming molten iron and aluminum oxide. But the thing about chemical equations is, much like a math equation, they actually have numbers. So they show us exactly how much of everything we need. Essentially, they are our ingredient list. They are the recipe, right? A cake doesn't look right unless you have the right amount of each thing. So, for example, in the thermite reaction, we have 2 aluminums that react with 1 iron oxide to form 2 irons and 1 aluminum oxide. If we had the wrong amount of ingredients, we could cause the reaction to either be too big or too small for what we need. So let's go ahead and take a look at thermite reaction in action. That's a lot of words saying action. I'm going to go ahead and share this with you up on the whiteboard. Here we go.
Talk me through what's going on, Matt. So instantly the thermite reaction starts, and you can see that it's so hot it's burnt a hole through the bottom of that terracotta flower pot. But if we go in close now, Brady, you can see all that really quite nice molten iron. Now that's so hot that the iron itself has melted and it's...
All right, tell me in the chat box, what did you observe? Again, we are going to go a little bit into passing period because of the start of class delay. So work quickly. What do you see? What did you observe in this video? What did you observe? Awesome. I see shelves in the chat box. Anthony in the chat box. Gabriel. Yeah, it's definitely not honey. Yeah, so it melted the bottom of this pot. These pots are actually nice because they're pretty good at holding in heat, but in this case it didn't work. It was way too hot. It's sizzling, there was fire, it created molten metal. Yes, very, very hot. It's essentially creating like lava here. Pretty insane. All right, let's go ahead and again, just a reminder that that is showing us, sorry, let me pop this up on our board again. And let's go back to our playlist here. Again, that is showing us that if we didn't have the right amount of ingredients, we could cause a thermite reaction that's way too big, which could be very dangerous. So we have to know exactly how much of everything we need. That is the point of a chemical equation. Please raise your hand when you have number 6 filled out with the word equations and only the word equations, and it is spelled correctly. You have 20 seconds to raise your hand. Go, work quickly. We still have 3 more slides to get through, I think. All right, we are waiting on Derek, Angelo, Casmer. Let's see here. Kamari, Tayan, Dion, Jaden, Patrick. Thank you. There we go. Okay, just waiting on, Annabelle in the chat. Waiting on Alexis too. Annabelle and Alexis. Annabelle, Alexis. Hello. Please respond. Thank you, Gabriel. Annabelle, are you there? Annabelle, I haven't seen you in several chats. There we go. Perfect. All right, Alexis. Perfect. That's 100%. Yay, good job. All right. So the last thing I want to just review really quickly, because we will be talking about these throughout our unit, are exothermic versus endothermic reactions, 2 words that you should hopefully be familiar with. So exothermic reactions will release heat, exo meaning that heat exits. Exo means exits. So in this instance, energy that gets stored in reactants gets released, and so the result is the product feels very hot. It's releasing heat into the environment. It feels hot. So an example is sodium and bromine will react. They'll create a lot of heat and light, and again, they'll also create something that's more stable. That's the point of a reaction, is to create things that are more stable. Sorry, you're just gonna have to stay until we finish up class, because again, we took way too long at the start of class to get participating. So you're just going to have to bear with us. Again, in the future, if we want to make sure we finish on time, make sure you start on time as well. All right, now endothermic, you can see a picture of that up here. I'm not going to show you the video because, again, we are running out of time. Endothermic reactions, on the other hand, absorb heat. What do you think endo means? If exo means exit, heat exits, what do you think endo means? I know, it's not cool for the rest of us, right, Ignacio? Yeah, it means heat enters, exactly. So endothermic, the heat is going to enter into it, which means it's actually stealing heat from the environment, making it feel colder. So I know that's a little bit weird to think about that it's absorbing heat, but it's actually getting colder. So as it absorbs heat, it uses that and it feels cold. So an example is ammonium thiocyanate and barium hydroxide octahydrate reacting to form a cool reaction. Now it's cool for two reasons, because it gets colder, but also it's awesome to look at. So this will be the last one that I show you. Let me go ahead and share this with you up on the board and get this ready to go. Here we go. Be ready to share observations, and again, share observations quickly. Here we go. All right, tell me in the chat box, what did you observe with our cool reaction, our awesome reaction? Our projects are going to be all about awesome reactions, by the way, our Unit 4 project. So this will be one of them that you can possibly choose if you want. What did we see? Yeah, it gets extremely cold. So interestingly enough, this is two powders that are being mixed together, but even two powders mixed together can still react. So we had these two powders mixed together, and they got so cold that the water underneath froze. This water was just plain water. The water had nothing to do with the reaction, but it shows how cold this beaker got from that reaction inside. So it got so cold that the water on the outside froze, and it froze the beaker to the wood, which is amazing. And most importantly, it froze it really well. It was able to actually pick up 20 pounds of books. I know, pretty crazy to think about. All right, let me go ahead and make this smaller and drop this back up on our whiteboard and move this back over. All right, here we go. Let me go ahead and jump back over here. So again, examples of both when you have really hot reactions versus really cold reactions. So that being said, let's practice this. All combustion reactions are going to be the same type. So a combustion reaction occurs when we have a substance that gets burned in the presence of oxygen, resulting in heat, resulting in carbon dioxide and water being formed. Again, different chemicals being formed. So for example, propane can be burned to form these different things. Tell me in the chat box if we are... All right, so all combustion reactions, what type do you think they will be? Endo or exothermic? Think about if they're releasing heat into the environment and feeling hot, what is this going to be? All right, so all combustion reactions exactly are going to be exothermic because heat is exiting, and the result is it feels very, very, very hot. All right, it feels very, very hot. So yes, so these are all exothermic. Heat is going to exit. It's going to end up feeling hot. Go ahead in the Q&A area, give me a smiley face, everyone, if that makes sense. All right, so the hotter it feels, the more exothermic it is. Hotter it feels, the more exothermic it is. Excellent, looking good, everyone. All right, let's go ahead and wrap on up here.
Provided examples for each reaction. We did this through our notes, so hopefully you got that in. If you did, shout out in the question and answers box how you did. At this point, we're going to stop our recording, and we are going to, Mrs. Larkin, are you good on your recording? No? Okay. Let me